Hi, my name is Greg Smith. I'm a professor of applied science and neuroscience at the College of William & Mary. Some students in cellular biophysics modeling had questions about what it means for a threshold to be sharp. So imagine you're recording the neuron membrane potential in current clamp mode, and you inject a brief depolarizing pulse of applied current. So this is time moving in this direction. That's the positive direction for time. And I mean this to be a square pulse of applied current. And we can call this time zero if we like, the time of the stimulation. Now the neuron membrane potential would be starting at rest, and that might be minus 65 millivolts or so. And when the stimulus occurs, the membrane will depolarize a little bit. Now, if a threshold for action potential is achieved, you'll often see a rapid change in the change in the derivative, a rapid depolarization of the membrane potential, and then a repolarization, and that is often followed by a hyperpolarized phase called the after hyperpolarization, and then you might go back to rest. So that's action potential stimulated by a square pulse of applied current. And the fact that we see this action potential means that the stimulation was super threshold. Now, what the sharpness of the threshold, what that phrase is getting at, is you can ask what would happen if there were a lesser value of the applied current, like say here. And in that case, the membrane potential would depolarize less quickly, and it might not even get over threshold. And the response might look more like that. Now, sharpness refers to how quickly do you make the transition between no action potential and an action potential. So imagine putting several different values of applied current here. And if you had the situation where each slightly larger value for the maximum of the current pulse caused an action potential to be a little bit larger in size, like that. And then with a little more applied current, perhaps you see this. That sort of phenomenon is referred to a graded response, because the peak of the action potential is changing dramatically as the applied current maximum is changing. That's a graded response, and a graded response is response with a threshold that is not sharp. So I want to write here that the threshold is not sharp in this case. Now, it could have been otherwise. So another type of response is often observed. Is that a depolarizing current pulse will lead to an action potential, as before. So let's imagine another super threshold stimulus. But now in this case, when the maximum value of the applied current during the square pulse is decreased, you may find that the size of the action potential does not change dramatically at first. And instead, the action potential remains full-sized. And it might just peak a little bit later in time. So now that was representing the response to this second highest applied current value. Let's do the next, a little lower. And maybe there's an even longer delay before the peak of the action potential. And then, of course, if the applied current is small enough, you'll be below threshold, and no action potential will occur. This is referred to as all or none behavior. And in this case, we would say that the threshold was sharp. Now, we haven't discussed this in class yet, but Hodgkin and Huxley observed both of these threshold phenomenon in the squid giant axon experiments that they performed, and they also were able to reproduce this phenomenon in their ordinary differential equation model of the action potential. And it's a subtle difference in model parameters that leads to this distinction, and we'll understand the dynamical basis for this difference in a few lectures. Hodgkin and Huxley referred to the graded, the all or none type of response as type 1. Okay. This is sort of an arbitrary notation, but this is type 1 response, and the graded type of response is referred to as type 2. Now, where exactly does this word sharp come from? What you can imagine doing is, in both cases, you could, on the horizontal axis, kind of put the applied current, and then on the vertical axis, put some measure of the size of the action potential. For example, maybe the peak. Meaning the most depolarized value for the voltage during the action potential. Now, in the case of the graded response, this peak increases with each value of the maximum of the applied current. So let me try to put that here. So the peak is changing. And at some point, there's a full-size response. Okay, so now I'm adding maybe more dots, and we actually have examples for the upstairs, but you get the idea. So in this case, the peak is a increasing function of the step in the applied current that led to the action potential. But if you think about what's happening with the peak in this case, the peak does not really change much initially. And then at some value of applied current, the peak just quickly collapses. Right? So this plot is going backwards. So there's the full size response, and then at some point there's just a collapse, and there's no action potential. Now I've tried to draw these so that the actual location where the response appears to be changing is sort of centered in the same location. And let me just sort of fill this in like this. And in the other case, you might see a response that looks like this. Okay, now the red response is graded, and the green response is all or none. When we say that the threshold is sharp in the case of the type 1 response, what's being referred to is that the range of applied currents required to move from full response to no response is relatively small. And in the case of the graded response, this range is actually much larger. So if you imagine the green and the red curves here as representing the corner of a table, the green corner would be sharper than the red corner, and that's where this terminology comes from. Notice also that it's in the type 1 response, the all or none response, where different latencies for the peak of the action potential are observed. The latency is referring to the time between the initiation of the stimulus and peak of the action potential. And you can see that this is about that long in the case of the first action potential, quite a bit longer in the case of the third full-size action potential. This time is often referred to as a latency. So the actual dynamical reason why these two types of responses are observed will come up in future lectures. But you may as well now begin to associate the phrase type 1 with all or none responses and sharp thresholds and the possibility of increasing latencies, meaning slow dynamics, and the type 2 responses with graded responses and thresholds that are not as sharp. I hope this helps, and good luck on your homework.